Okay, welcome to video 8.3. Chapter 8 is actually a big chapter, so not only does it cover molecular geometry, that's really just the starting point. Once we have a sense for geometry in three-dimensional molecular shape, we can start to think about how orbitals with their individual shapes overlap in space, and that leads us into bonding. And bonding is really a big topic because there's multiple models for bonding. We're going to talk about three big bonding models. We're going to start with valence bond theory, and this is the simplest model. So we're not going to spend a ton of time on it. It's pretty intuitive. We're going to build on it and add a little bit extra complexity, which helps us describe real systems. So valence bond theory really states that bonding occurs when a singly occupied orbital overlaps another one. And so singly occupied orbital overlaps another one. And then, so I'm showing you the simplest version of that, which is the singly occupied orbital, the 1s1 of hydrogen and the 1s1 of another hydrogen. These two things can overlap in space symmetrically because they're spheres, and they give us this nice looking hydrogen molecule. There's a couple criteria here that we need to define. We alluded to this when we talked about quantum mechanics and the shapes of orbitals in a previous chapter, but the orbitals, they have to have the same phase to overlap. And remember, s orbitals like this, they're completely spherical and they're all one phase, and so that's easy for overlap. But when we have things like p orbitals, remember that p orbitals actually had the two different phases. One was positive, one was negative, and that becomes really operative here. We need to make sure that when two singly occupied orbitals overlap, they're overlapping with the same phase in order to form a bond under this simple model, this valence bond theory. The other criteria here is that the greater the overlap volume, the stronger the bond. And that's a big one. And actually, that's true in all bonding models, not just valence bond theory. But if you have a bigger overlap here between the orbitals, then you have a stronger bond. So that means double bonds, triple bonds, they have larger overlaps of orbital volumes than do single bonds. And so if you go on to take a physical chemistry course or a quantum mechanics course, you'll actually do a three-dimensional XYZ orbital integration to evaluate what is the volume of this overlap, which will give you a direct quantitative measure of how strong that bond is. Let's think about a more advanced example here. Let's think about the bond that forms with valence bond theory as a model between two fluorine atoms to make the F2 or the fluorine gas molecule. So let's think about first the fluorine atom inside of this molecule. It has an electron configuration of helium closed shell, 2s2, 2px2, 2py2, and 2pz1. So it's got a total of 5 electrons distributed over those 3p orbitals. In this case, there's actually only one electron that each fluorine has that can satisfy this valence bond theory criterion, which is that the singly occupied orbitals are the ones that overlap in space. In the 2px and the 2py, those are both fully occupied, and so those don't overlap. They don't have space to overlap with anything. And so the only thing that we can overlap is the 2pz orbital, and that's exactly what we see when we form that single covalent bond between fluorine atoms. We have the singly occupied 2pz here and the 2pz here, and those two can come together to overlap with this volume and form that covalent bond. Similarly, we could look at the HCl molecule. We know that HCl the hydrogen in HCl, it's got that 1s1, so it does have that that one unpaired electron. And then Cl, it has the same electron configuration as fluorine. It's just got the 3s2, 3p as its structure. So in the end, it also has then this 3pz that has one unoccupied space. So those two could come together because they're singly occupied, they overlap, and now they form this bond here. That's our covalent bond between these two atoms. So there are a few takeaways from this general model of valence bond theory. I'm just going to write it as VB theory. One we've already talked about, which is covalent bonds form when you have overlap between atomic orbitals, and we're calling atomic orbitals those orbitals that reside on the individual atoms. So in this case, above for HCl, we had a 1s atomic orbital on hydrogen, and we had a 3p Z atomic orbital on chlorine. Those two things overlapped in space to form covalent bond, and we needed one electron unpaired from each to form that bond, and they had to be opposite spin electrons, same phase orbital, right? So the same phase here comes from this idea that I didn't mention this explicitly, but we can see that here. Chlorine, the p orbital on chlorine looks like this. This whole thing is the p orbital, both dumbbells, but one side has a positive phase, one side has a negative phase. So the actual bond that forms with hydrogen has to have the same phase to actually overlap. So that's the first sort of implication of valence bond theory. Covalent bonds overlap between those atomic orbitals. Something that may not seem that important, but really is, especially when we start to contrast this to other theories, bonding theories, is that each atom, it maintains its atomic orbital, its own atomic orbital, I should say. In other words, orbitals, the atomic orbitals on those individual atoms, they overlap in space, but they don't change or distort in any way. They remain their individual atomic orbitals, which we're going to see in future models doesn't always have to be true. We also then determine that larger overlaps of orbitals, that's a stronger bond. So those are the sort of big takeaways from valence bond theory so far.